like all chapter ones are pretty much the same for database books. Microsoft Access is a relational database model. Most of the popular, widely used database systems are relational models. There are object-oriented models. There are other names for non-relational models, but I've only ever used relational models. The other ones are more specific, special purpose, or just not very widely used. So what we learn in this class, the way that we're designing these tables such that rows within them can be combined with rows in other tables, is typically how most database work tends to be done. There are some free database systems, MongoDB. What I say for most of this semester, just basically pertains to this common standard relational model. This thinking about the project that we're working on, I'm having you guys currently steal data off of websites to compile this airfare data, right? Are any of us at all afraid that we might eventually one day be prosecuted for stealing data like this? It turns out, at least back in 2019, maybe the Supreme Court has reversed that by now, but it's completely okay to steal data that has been put in the public sphere. I think that is why the airfare companies go to so much effort to prevent those $276 fares that you're collecting for me from ever appearing in the source code of those HTML files. If you look at the pages that actually display the prices that you're copying down right now, they are not in the source code. Wouldn't it be much easier to collect this data if it was just in the text file, under the HTML text file underlying the page that you downloaded to your machine? I mean, the data is getting to your machine somehow, but it's being sort of dropped into the mad libs of that page somewhere above the level of the HTML file. So for people who are in web programming, this is completely different from what we're used to. Those values are probably being transmitted in through some JavaScript script or something over the internet, but it never goes through that text file where it can be copied. Because once they put it out in the public domain like this in response to a query, it's legal for anybody to use and copy down and whatever. So that's what we're doing. In fact, that's what we're doing in web programming. When we were copying down the details of past games being played and the moves in those games. That slides.google.com actually prints out a graph of your historical record of flights, and so people were thinking, you know what? I don't need to collect data. I'm just going to copy paste that graph into the homework. I think the graph looks more or less like this, right? But
I mean, I don't know, it's probably accurate. There are some things I don't like about this graph, like, where are my x-axis values? I can't make them weights or anything. So this is a poor substitute. I wouldn't go forward with the assumption that you're going to be able to use Google Graph. You don't have enough control over Google Graph. It's better for you to collect the raw data yourselves and then make an actual pretty graph in Excel that you can paste into your Word document. So I'm trying to correct my mistakes and student assumptions from the past to make sure that we get the most out of these assignments here. All right, I think for the rest of the day I'm going to leave my crazy project stuff and, let's talk about theoretical database because in my experience that's what led to the theory. Love the theory. So, as we know, we organize our data into our databases, generally in the form of tables. The columns in these tables are named. We tend to call that attributes in database land. When we're talking about objects, we might call those things properties. But basically, they are the column headers in the tables that we view in Microsoft Access when we're doing these spreadsheet views of the content of the table. And you might recognize that each individual row in whatever table you're looking at is basically collecting the values of the attributes, and they're related in such a way that it sort of makes sense. It sort of creates an entity of whatever type that table is trying to represent, whether it's a student record, or a course record, or a time slot record, or a department record, or a building on campus record. Basically all of the data about the buildings on campus are typically arranged in the same row with the name of the building in question, that sort of thing. That gets used in all of the tables. Every row can be considered to be an individual entity with all the related data contributed to it somewhere on that row. That's usually how tables are designed. So those structures, those cities, those courses. If you've got a transcript table, that might even be a row that considers the list of courses, although probably since everybody has a different number of courses in their transcript, it's probably more common that we just combine a whole bunch of courses with the course row together into a customized or if you take a student, pull out all of the rows of courses taken by a student, arrange them by date, semester, or something like that, and then make a big combined as many times as you need it to. It looks kind of needlessly complicated when you're looking at the SQL, but that is probably a valid way of making, well, it is a way of making a transcript record, I guess. I probably wouldn't do it that way. There are probably systems. I guess what I'm doing here with these definitions is I'm sort of building up to why we call this arrangement of data and relational database structure. Since the rows of these tables represent related items, that these items are related together in such a way that they describe a particular entity, those values. And of course, the values that we see on a row of a table, we're looking at the multiple structure of the database. Again, like I said in class last time, I believe, just because two values are adjacent to each other in the row in the table doesn't mean they're adjacent to each other on the logical structure. It doesn't represent physical structure. We manipulate the logical structure to make it understandable and pretty to us.
since a table represents a collection of these relationships, when we talk about this idea to the mathematicians who want to build mathematical models for us that will help us do our operations quickly, efficiently in the database, when we start programming a new database application, the idea that already existed in math of a relation is something that they adopted, and so that idea came from mathematics based on our idea of relationships back into the universe of databases. And so that's why we call our current common system of arranging data in a database a relational database model. But when we start talking about the theoreticals, the theory, mathematical theory underlying and trying to represent things mathematically in our applications, we're going to see some mathematical notation that comes from the area of representing relations in math class, relations between values, connections between numbers that need to be associated for whatever reason.
Is there a word for rows, like columns or attributes?
Yes, I'm about to come to it. It's going to be tuple. Yep. A tuple is basically the mathy way of saying, I have multiple values on, a list of values here, and that's what we're going to call a row eventually. When they say an n tuple, they're basically saying this row has n columns in it. If we have a table like some of our glue tables had only 2 attributes in it, 2 columns in them, those were 2 tuples. Those tables, every row had 2 attribute values on them. So, I'm basically just assigning technical mathy terms to terms that make a whole lot more sense to us when I talk about a relation, or when the author, really, because I tend to use the more common terms too. But when the author in the textbook talks about a relation, he's really talking about what we refer to as a table. When the author talks about tuples, he's really just referring to a row of n values. And when the author talks about attributes, he's really just talking about the column headers, the names at the top of those columns. And again, I keep on referring back to how we design objects in our object-oriented programming classes, and attribute. An attribute, when we're designing an object class, we might call that a property, or a member variable of that object. And so a table can be seen as a list of objects declared in a program. Every row is all of the values stored in each individual object that has been instantiated within that program. I talked about instance before. I think I said instance is like snapshot. So what are the current data values in whatever we're looking at here? If we're talking about a relation instance, since relation means table, we're talking about all of the data that is currently in this table. And of course, this is just a snapshot for a particular instant in time, because data in tables is always changing. Once you make another order on Amazon's website, then whatever table is holding your orders has now been changed. It has at least one new row in it, probably. And you're not the only one submitting orders to Amazon. So that orders table is constantly changing. When I refer to page numbers in these slides, these are slides that were provided to me by the company that published this book. And so I always modify these slides, of course, but like 80% of them are what was provided to me. When they refer to page numbers, they're referring to page numbers in the printed book. I don't know, sometimes that doesn't match the page numbers in the digital copy of the book. I don't know if there's even is a digital copy of this book, but I guess I would be surprised if there wasn't. So since what we're looking at when we're looking at the contents of a table is the logical view, then that means that the view that we're looking at, sometimes we have the data ordered by a particular column, and so the order of tuples in a table is basically irrelevant. If they're in a different order, they still represent the same relation. They're still the same table, right? They are still the same snapshot of data, no matter what their order is. Order is something that we change in our logical view just because we want to see all the names in ascending order, or all of the items in sorted order by item ID or whatever it is. And so, at least in a mathematical sense, and mostly in an everyday sense, order of rows in your table is largely irrelevant. It doesn't change the identity of the table. It doesn't change the contents of the table. The data is essentially still the same. So here's an example of what your book author will call a relation. You can recognize this as, this is just a table. This is the spreadsheet view of a table. This actually comes from all of the tables that I show you, at least the ones that are blue and white here with this color scheme, match the database schema handout that I gave you a week or two ago. And so somewhere on that handout, you're going to find I don't have this table named, but I can see that this is the names of professors at this university that database represents. And so this is a snapshot. What's the technical name for snapshot again? I've already forgotten. Instance. This is an instance of the instructor table. And so if you looked at that handout, you would probably see a rectangular box named instructor, and it has 4 rows in it. It's going to say ID and name and department name and salary. It's telling us the structure of the table. And now we're showing you what the contents of that table is. If this table were representing instructor objects in our object-oriented program, these would be all in our Sim University program that we just wrote. Then these are all the instructors wandering around campus. There's an instructor named Mozart who teaches music, or at least is associated with the music department. There's an instructor named Katz who is a computer science professor, their salary, etc., etc. A lot of these values are hidden inside these objects. When you're playing Sim University, you don't necessarily know that Professor Katz is making $75,000, but that is a value stored inside that object while the application is running. And maybe there are ways for you to access that data. I don't know why I'm talking about objects again. This is database class. I should be restricting my conversation to relations and attributes. So we've got attributes, those are the column names. We've got tuples, those are the rows. Okay, I guess that's it for that. Let me do some more mathematical background. Remember in math class when you were talking about domains and ranges of numbers? So domain also has applications in our programming classes. We have domains for data types. You know that if you are declaring an integer data type, then all of the possible values for your integer data type are going to be numbers without decimals, right? And your hardware limits you to a specific range, but in theory, we're talking theoretically here. We're in math world here. In theory, the domain of an integer attribute is all whole numbers without decimals from negative infinity to positive infinity, right? We can't represent all of those in a computer because a computer, by definition, is composed of a limited amount of hardware, and so it's going to run out of memory space eventually. But in theory, the domain of integers is all whole numbers. The domain of floating point numbers is even larger, infinitely larger, I guess. What is the domain of strings as we know of them in our programming languages? I guess a collection of characters up to size infinity, in theory, and you know, all possible combinations of characters from length 0 strings all the way to length infinity strings would be valid values that we could store in a database that had an attribute of type string, right? And we know that Microsoft Access has short string, long string data types. Is it called string? Probably, I forget. Generally, in a database, at least when data is being retrieved from a table, data is considered to be atomic. That is, we don't expect that data should only be retrieved in part. We shouldn't retrieve half of a data value out of a field. So I guess there's probably going to be I think, oh my God. Okay, now let me go back then. I had an example in the back here. So for this table here, like what I'm saying by the salary values should be atomic. When these salary values are being retrieved, we're not only going to retrieve the first half of the number, or even worse, we wouldn't retrieve like only the zeros half of a number. That would be a terrible salary to be paid. If a value is being retrieved, the whole thing is being retrieved or not. That's what atomicity means, is at first, you might manipulate things later, you might take things apart one character at a time later, but when data is being transmitted to you from the database server, it's transmitting all of the data to you before you start your manipulations of it. That's atomicity, and that same idea applies to transactions that have to go through completely or not at all. Databases consider that there is a special value null, just like most programming languages, that mean no value has been assigned to this cell to this attribute in this row. And the reason for that, I mean, it's the same reason that zero sometimes causes complications in math world. I mean, if we combine numbers in certain ways and end up dividing a number by zero, then we don't really know what to do there. So sometimes there are things that you can do. Maybe you're trying to combine data together, and if you have to combine data together with a null value, the same sort of weird error pops up where you can't combine nulls with strings or something, because null is not part of the same universe. And null has its own domain, which is not the same as the domain of strings, and so you can't combine those data types in such a way that makes sense in either of those domains. So it doesn't, it's not the end of the world if for some reason you retrieve data and some of the cells in your retrieved table are empty or have null values. It just means it could just mean that a faculty member has been newly hired and maybe we don't have all of the information for them, or a student is a new student at the university and the university office doesn't have all of the data for them, but eventually they will get it. It's just that if ever later there are some operations that require knowing the address of a student, those operations may fail because there's a null value that's in a slot that is required for an operation to complete. So that's all I mean by saying the null value can cause complications. And so that's why we often, in writing our code that deals with database values, either want to write our SQL queries in such a way that it minimizes the possibilities of nulls appearing in our result set that could cause problems down the road, or we're going to have things like if structures that only deal with the values that don't have nulls in particular attributes and process only the data that won't crash whatever process, whatever function we're writing in SQL. All right. So a database generally has multiple tables in it. Our airfares database will not. I'm having you collect everything in a single table. I think I told you to track every flight on a different sheet of Excel, and that's just to make things easier, hopefully, for you. But when we gather all our data together, I'm basically going to have you take your 3 Excel sheets and concatenate them all together, and then that will be concatenated to everybody else's concatenated tables. And so we're going to have all of our data in a single table. That's usually not a great design, but all we are tracking is a single entity. What is the airfare on this date, and what is the identity of the airfare? Oh, it's from MSP to DFW or MSP to whatever, and it's this flight number by this company. So that's the entity that we're tracking, and we haven't yet come up with any reason to need any other entities in this database. That would require me having you track other information, probably, although most of that information might well be just write that data down once, and that's a row in a table, and that's all you need. Maybe you'd have 3 rows in your table because of your 3 flights. But anyway, that hasn't seemed helpful to us. But most databases that are representing something relatively complex in the world, like a university campus, is going to have multiple tables representing multiple entities. We're going to keep, for example, the instructors separate from the students, because we track different data for instructors than we do for students. Instructors, for example, have salaries. Most students aren't necessarily being paid by the university. Yeah, that's probably a simplification. I know that some people are being paid because they have some sort of student jobs, but we're going to assume that our student records don't have a salary attribute, mostly because probably a majority of students don't have campus jobs here, so that would be a good enough reason to create a student worker table somewhere else where that attribute would apply to all records in that table, whereas they don't apply to all students in the general pop student table. An advisor is basically a combination, if you look at your database design handout, of the IDs in the instructor table and the student table. And so basically it's a glue table in this case that glues together all of the details of instructors with the students that they advise. So, like I say, if we were to try to do for this university database the same thing that I am having you do for this airfares database, and if we were just trying to put all of the data that the university needs in this single table named university, it might be something like a great big massive concatenation of all of the attributes from all the tables on a single row. And I don't know that that would necessarily make a lot of sense, because when you're inputting student information into that row, probably you don't need like building information about buildings in the buildings on campus. And plus, again, like I said, a lot of these students don't actually get a salary from the university, and so that would be another field in the row that would be empty. And what did I say about null values, empty values in rows? We like to minimize those, right? And so another good reason for splitting up a database into multiple tables is it does help us avoid having empty values in our rows. And so, yeah, and I don't even really have a good idea of what this university table entity would be if it had instructor IDs and instructor names and department names and salaries and student IDs. I mean, already that's probably a contradiction, except for maybe instructors who are students in a class or something. But I mean, that's not going to apply to a whole lot of people. And so the trouble with this kind of design is it's the intersection of too many concepts, and most of these fields won't apply to whatever concept we're trying to represent in any one row. Does that make sense? Or did I lose you several sentences back? So generally, a single table database is a bad design, unless really the situation we're trying to represent is so simple that it doesn't require more than a few attributes to represent anyway. Because yeah, other reasons why this is a bad design, either we're going to have a whole bunch of null values, or we're going to have a lot of, remember how string values are the most expensive values to store in a computer system or in a database row? And we're going to have a lot of string values in this, this great big massive schema here for this table. And so that's already a pretty big reason for not, and a lot of those strings will be repetitions of the same string. If you look at the design of that university table, if all we're doing is concatenating together a bunch of schemas, sometimes there are repeated string values between those tables, and so again, we'll be wasting space. We won't be, we'll have a whole lot of empty spaces, a whole lot of null values in every single row of this table, and it's just not going to be a very efficient way to store our data. We end up using less space, and we end up with less null-based problems if we define all of our tables separately, just like when we're writing our object-oriented programs, we use multiple data types. Even when we're creating our own data types, we don't put all of our data attributes together into one global object. It just doesn't make sense for most of what we want to do in any of our programs, no matter how complicated or simple. We don't just use one data type. So normalization, I usually don't get to chapter 7 in this class, and I think that normalization theory is boring. So normalization theory does deal with how to design table schemas as efficiently as possible, and it has multiple levels. Level 1 is fairly obvious, it's what you would do anyway, and then there are increasing levels of complexity that are supposed to streamline your design more and more, but then my eyes start glazing over, and so I'll let you guys look at that if that appeals to you, but we usually run out of time before we get to that because I'm making you print so many airfare graphs or something, and do presentations on them. Crafting predictions, if the airfare has been going in this direction for the last 3 days, what will the airfare be tomorrow? Should I wait to buy the ticket or should I buy it now? All right, so when I talk about schema, I'm basically talking about all of the data values that will be on a given row, and generally what their data types will be. I'm talking about the logical design of the database. I'm talking about what that database will look like in its spreadsheet view when it's being represented on your screen. I think I've talked about instance. You already know it's a snapshot of the contents of either a single table or the entire database at any given instant in time. And this is just me talking about object design again and how it's so similar to database table design. The schema for the department table. So I call this a single line schema. I might refer to this in a homework as SLS. That's short for single line schema. But basically, it starts with the name of the table, and then in the parentheses are the column names within that table. So a representation, an instance, a snapshot of the current values of the department table in your university database, as defined by this single line schema, is a table with 3 columns. The first one is department name, the next one is building, the next one is the amount of money that's the yearly budget that is assigned to each department, say, and by the business department, or the business office of the university. Wow, I don't know why my laser is so terrible on this clicker. Maybe it's getting old. But okay, what this is telling us, what this department table is telling us is that biology must be housed in the Watson building, and they get $90,000 that they can spend on materials per year. Computer science spends $100,000, and they are housed in the Taylor building along with the electrical engineering department. Finance and history are both in the Painter building. Music is in its own building. Hey, physics is also in the same building as Watson. That must be the science building. Or I mean, at least the natural science building. Computer science and electrical engineering were like the artificial science, technical science, application science. Any questions? This all makes sense? Trying to introduce new vocabulary that you're going to see the author refer to and show you what it refers to in terms that you understand, that you're already familiar with. Why am I using instance instead of table? To get you used to it. Or instance instead of snapshot, I suppose. Oh, here, formal definitions. We're getting even more mathy. So we know that attributes are going to be strings, string values. They're the names at the tops of columns, but mathematicians, of course, will say, okay, well, I know that this table is going to have a bunch of column names. I'm just going to represent them with the variables a sub 1, a sub 2, a sub 3, all the way out to a sub n, where n is the number of columns in your table schema, in your table design. A relation, R, is going to consist of particular values, A1, A2, A3, basically all of the values that you see in each of the columns from right to left inside that table. We're going to call that a relation schema. So the first attribute value is going to be A1, the next one is going to be A2. Actually, I guess those are column names. And so I guess a relation schema is going to be the design of a particular row from a table, but it's basically the same as the names of the attributes at the top of that table. Although the order of the rows is something changeable too, because sometimes we may want to see the instructor or the student name first. Sometimes we might want to see the student's tech ID first. And so we can manipulate that in our SQL queries. And so whatever we see as query results or table displays is really still a logical view. It is kind of programmed by code or by the SQL query that we gave the computer to say, show me data in this format, in this arrangement. Types will have particular domains, and so given sets of domain values, a relation R, what is relation? It's a table, right? Any generic table R composed of a given set of domains for the number of columns that it has. A relation R is a subset of all possible values, valid values for domain 1, times all possible values of valid domains for domain 2, valid values for domain 2, times all possible values for every domain all the way out to, times all possible values for the valid values for domain number n. What we're basically saying is a theoretical table could for these domains could have all of these possible values, and they're even putting all the nonsense strings like AAAZY is possibly one row. And so these are tables that are not of infinite length necessarily, but in theory I guess they could be, since we could have strings of infinite length. But technically we're saying if you design your Microsoft Access table with a short string attribute, say, so a string that is at most 255 characters, then theoretically there could be a table with any value that's 255 characters in it or less in this field, and the theoretical table has every possible value for every attribute in every row. That's going to be a lot of rows. And so we're saying whatever table you're currently looking at comes out of that set, but your table only has like 200 rows or 20 rows or 1,000 rows. And so it is a subset of all the possible rows that could be in a table with this design. Does that make sense? Why do we care about that? Well, we don't. But mathematically, these are the things that they set out is, here is the theoretical table of that design with all possible values in it, and then your table is just one of the possible subsets that we could draw out of that. So, any given table is just a set of tuples with n columns in them, with these values, where each value, and this is not column names now, these are actually the values inside those columns with those attributes, where each value is a valid value from the domain of whatever data type is being stored in that column. So the current values, the current data currently stored inside a table are called a relation instance, a snapshot of the current values inside of the table. Any given what is R? R is actually the design of the table there. So any element coming out of object R is basically going to be an instance, a row out of R, right? And so we call that instance T or element T because we know that it's a tuple, and that's represented by a row in the table. Okay, I guess maybe that's enough mathematical definitions. Again, I'm exposing you guys to this just because maybe if you're reading that book, or if I gave you an assignment where you have to read the book to figure out what to do, there are some sections of this book that go into this mathematical technicality, right? So I want you to see how stuff is represented in this book from time to time. Also, I mean, they just gave me this slide in my chapter 2 PowerPoint here. And so I thought, well, if you're going to use something out of chapter 2, maybe you need to see how things will be expressed. I prefer views like these. Views like these make more sense to me. So, relating relations. This is exactly what I had you do in your, I think, first homework or second homework, where I had you create 3 tables and then glue them together, right? So this is an example of a possible snapshot of the data inside your university table design here. I have an instructor table with all of the faculty that are currently employed by the university, and I have a list of all the current departments where courses are being taught in the university. And if somebody comes along and has the query, I want to know all the names of all of the instructors, or I want to know all of the information about instructors who work in the Watson building, I can't get that information just by looking at the instructor table, even though that seems to be the subject of this query, because the information about where those faculty actually work is actually in the department table. But we can get that information by combining these 2 tables together, right? And so when I asked you guys to come up with a situation that required combining 2 tables together, gluing them together in order to represent something, this is an example of that sort of situation. If we want to figure out all of the instructors who work in the Watson building, and we have this data set right here, what we would have to do is glue the rows from this table concatenate them onto the rows of this table, but we would only glue these rows onto these rows where they have a value in common. And the only value in common that I see between these two schemas, basically collection of attribute names, is department name, right? Dept_name. And luckily, because this is not always the case, but luckily the type of data in the dept_name column in both of these tables is exactly the same, comes from exactly the same domain, right? I'm not saying just they're both string types. I'm saying they both represent their data in the same way, because what's another way of representing departments on a campus? This course is named CS 3507, right? The CS stands for, this is a course from the computer science department. So that we could also represent computer science stuff by saying instead of computer science, we could say CS, PHY is physics, math is MAT or whatever, music is MUS. And if the department table were representing their department names with all cap 3 character names, then we would have no common data to be able to tie these tables together with. But since both of these department names actually store their department name data in exactly the same way, we know that we should be able to look for values where in this row where department name is biology, and then I'm just going to concatenate this row to the end of that row. So yeah, one biology. That the result, the query, the table that query will build when it delivers that back to you will basically be a concatenation of these two schemas. It will be instructor.id and then name, and instructor.depth name and salary. I guess I didn't need to pretend ID with instructor because there is no ID here. And so it would be ID, name, instructor.department name, salary, department.department name, building and budget. It would basically just be a monster table created by the concatenation of the two schemas. Right? And so this data would be appended to the end of this row and no other rows. Computer science data, this row would be appended to the end of this row and this row and this row. Electrical engineering, well, you get the idea, right? Would be appended to that row. Finance would be appended to that row. And this bottom row down here, tell me if I miss a row. I'm just going to be anal about this. History is going to be appended to this row and this row. Music will be appended to this row. And physics will be appended to this row. Did I miss any? I don't think I missed any. I think all of these department names are in here at least once. And all of these rows have a value that is represented in this department table at least once. And that's the kind of design I wanted you to build in homework 1. So that you could look at this example and think to yourselves, yeah, I kind of built something like that. I think I suggested to you that you should use IDs to glue things together, and that's not how they're doing things. They're using string values to glue together. And that's fine, that works, as long as we know that those string values will never be misspelled, because if for some reason I have physic in one table, then those two rows will never be appended to each other. But that is also why when you're entering data on websites, that if you only have a limited number of string values, those values are in a drop-down box where you just select the value from the drop-down box and you're not typing it in. That's how they avoid getting misspelled values in their databases, which would prevent their table values to be combined when we need to combine information from multiple tables. Does this make sense? Again, when I gave you that homework 2, it just came out of the blue. It was basically to prepare you for this idea here, right? Hopefully, you now understand this idea better having done it than you would have if I hadn't had you do it before you saw this slide. I think that's all the time I have for today, so I will just go ahead and dismiss you. Thank you very much for showing up. I will see you guys back here on Monday. Have a good weekend.